Hello, my name is Vince Purcell, and for my project, I will be predicting MLB game outcomes. I'll start by giving an overview of the project. So, project objectives. I want to collect data using MLB's Game Day API, and then I want to perform sensitivity analysis to determine the importance of various pitching and batting statistics. Then I want to analyze various models for accuracy in predicting the winner of MLB game matchups. So quickly, I want to go over the importance of this project. If you've ever seen Moneyball, you've heard of sabermetrics and the importance of data analysis when it comes to, well, specifically MLB teams. MLB teams would like to know the probability of their team winning based on different batting lineups and different pitcher matchups. Also, at the time of this presentation, sports betting is legal in more than 24 states, and one could assume eventually it'll be legal in almost every state. What is original about my project? I decided to use MLB season stat predictions. Most research I investigated about this topic would use running averages, which intuitively that makes a lot of sense. But after looking at all the research, I wanted to do something different. I also decided to include umpire statistics into the predictive model to see if there was an effect. Now I'll go over the data collection processes. Data collection approach. I attempted to collect box score, game summary, player data, and player stat projections for each MLB game matchup over the past 4 years. To do this, I used the MLB Stats API and the MLB Game API Python packages, and I also had to use HTTP requests to access this data. The reason for using multiple avenues of data collection I'll go over in the next slide, and I stored all this data into a MongoDB. Problems I encountered during data collection. The MLB Game Day data was incomplete for a large portion of the games. That's why I said before that I attempted to collect data for the last 4 years. If data was incomplete, I would scrap it. I didn't want to have incomplete data used for data analysis and predictions. Also, the Python API packages that I used, the Stats API and the MLB Game API, they had existing issues or they didn't implement certain functionality. So that's why I had to use both, and I also had to use HTTP requests. But using those 3 methods, I was able to get all the data that I needed. So database choice. Like I said before, I use MongoDB. Firstly, just because I'm most familiar with it. Also, MongoDB synergizes real well with the JSON outputs of the APIs. And using the pymongo Python package, it makes storing and accessing Mongo documents immensely easy. You can simply just dump JSON outputs with one line and worry about it later. And at the time of data collection, I was unsure of what specific data points I would be using. So I took the approach of just collecting as much data as possible and then worrying about that later. So now I'll go into the data analysis portion. So now here's a quick overview of my approach to the data analysis. Start with data preparation. Then I'll perform sensitivity analysis on regression models. Then I will analyze various models for accuracy. And finally, I will create a procedure for predicting future games. So I'll start by going over the data preparation. So, data preparation. I'll start by reading all the MongoDB collections for batting and pitching projections for both home and away teams. I also included who the home plate umpire was to see if it had an effect in prediction during sensitivity analysis. And the target column will be whether the home team won or lost the game. Here is an overview of the training data. The data collection script that I wrote collected data from 1,202 matchups, and I performed a 85-15 training test split. And from the pair plot on the right, you can see that the data is definitely not linearly separable. I only plotted 4 data data points, but there are many more. But I did find it interesting that each data point had two peaks, and I think that's due to there just being a clear two tiers in teams when it comes to batting and when it comes to certain pitchers. And on the bottom left, you can see just a count of home wins and home losses. There's a slight skew towards the home team winning, which that makes sense to a degree. So like I said in the last slide, there are more than 4 data features, and in fact there are 97, which is certainly too many to put into a predictive model, and all features may not prove to be influential. I will now go over the sensitivity analysis on regression models portion. Quick overview of my approach to the sensitivity analysis. Firstly, sensitivity analysis is done to quantify the relationship between model performance and dataset size or data features. I will perform sensitivity analysis on support vector, multilayer perceptron, and decision tree regression models. The end goal being to only include data features that prove to be more influential. And the sensitivity analysis will help me determine which features to leave out, and that'll cut down on dataset size. Here's the sensitivity analysis for the support vector regressor. As you can see, the most influential data points were the projected pitcher outs and also the TPA average, that is total plate appearances, and also pitching strikeouts. And interesting point is that the umpire ID is actually included in here. So it's the 7th most influential data feature out of 97, which I found interesting. This is the sensitivity analysis for the multilayer perceptron regressor, and you can see that home and away pitching PA projections was the most influential, and PA is pitches thrown per plate appearance, and the outs also appeared, and the batting TB average, which is total bases gained through hits, and again TPA, total plate appearances, and also home pitching IP and away pitching IP, which is innings pitched. Here is the sensitivity analysis for the decision tree regressor. This one ended up differing from the past two in that it found different data features to be more influential. The first one being the pitching statistic WHIP or WHIP, which is walks plus hits per inning. And when I looked this up, this is actually one of the most commonly used statistics in determining a pitcher's performance. And then the other more influential ones was win percentage for pitchers, pitching hits, pitching wins, and then the OPS batting average. So OPS is the addition of on-base percentage and slugging percentage. So it was good that the decision tree regressor found different data features to be more influential. So after using the input of the sensitivity analysis for the 3 I just went over, I was able to cut down the data to only 33 data features, which is much more reasonable to use for predictive analysis. Now we'll analyze various models for accuracy. I started with SVM and MLP, support vector machines, and multilayer perceptrons. Both models either predicted all games as win or losses, so not very good, but the data was not linearly separable, so I somewhat expected this, and here's a confusion matrix showing that. Now we'll go over the decision tree model. Decision trees seem to be best suited for this data set. They performed better accuracy, and unlike the SVM and the MLP, I found that a decision tree with a max step of 3 performed at 69% accuracy. If I didn't include a max depth, it actually would perform at around 60% accuracy, so actually cutting down on that improved it. And there was a great Python package I found called dtreeviz for decision tree visualization. The link to that package is on the bottom left. So as you can see here, this is actually the output from that package. It displays the distribution of each statistic, and the arrow is the deciding point, so if it's less than or equal to that. And at the bottom you see these pie charts that show the distribution of losses or wins at the end of each decision tree point. Naturally, getting good results from a decision tree, I moved into random forest. I found that a random forest with a max depth of 4 and an entropy criterion produced the best results. Here is a visualization of just one of the estimators. I ended up using 150 estimators, and I got over 70% accuracy for random forest. Now I will go into the procedure for predicting future games. So I stored data in MongoDB collections separate from training data in order to not interfere with model training. Also, I found that MLB game day data is available for future games, but only at most about 3 days out. They don't predict starting pitchers or batting lineups, so when that data is available, they update it, which I'm assuming. After running this on a few days throughout the month of August, I found it will get anywhere between 55 to 80% accuracy. Here's a sample output of that script. I'm recording this presentation on August 22nd, and here is the output for today, and these games have not happened yet. So, like I said earlier, at the time of recording this presentation, sports betting is legal in more than 24 states. So of course I'd apply this model to a sports betting scenario. The best option in my opinion would be to do round robin betting. Round robins are parlay bets that bet every combination of parlay that you specify. So here's a scenario where it got 60% of the games correct in predicting the outcomes. And I have the parlay size as at most and 4 times, so it's going to create a parlay of 4 teams and every combination of those 10. And in this situation, you would only gain $9. So this should be the lower echelon of what you should aim for. Here's a scenario where you got 70% correct, and in this one, you'd gain $205. And here's the upper echelon of the model. This probably would not happen often, but here is a scenario where it gets 80% correct. You would gain $523. So in conclusion, for any sports predictions, any model worthwhile will need to be at least 65% accurate. Decision trees and random forests are most likely the best solution for any data science problems that involve sports statistics and sports predictions. And any of the code for this can be found on my GitHub, the link on the bottom left. And thanks for watching.